Please be careful. You don't want to be in the way when my laser goes off.
Hey, a laser? How come you don't have a laser, Woody?
It's not a laser. It's a little light bulb that blinks.
What's with him? Laser envy.
Okay, that was my tribute to Toy Story celebrating its 20th anniversary. What we're going to be studying here is laser light versus ordinary light. So don't forget, the ordinary light, you've got a mixture of wavelengths if it's white light, and if it's even yellow light, it might all be the same wavelength, but those wavelengths will not be in phase with each other or won't maintain a constant phase relationship, so they're not coherent. Whereas laser here, you can actually see it maintains a constant phase relationship. So here you've got them all meeting crests and crests, so you've got nice coherence there, in phase with each other. But not only that, the waves following behind it will also be in phase at this point, when they get to this point. So you've got good temporal coherence, so each wave, one behind the other, actually matches when it gets to this same point here in terms of phase. And that's why it's good temporal coherence. So let's look at some examples of that here. We've got a real laser in the lab here reflecting off some smoke particles, so you can actually see it, and have a bit of a nose at that. Okay, let's just have a look at lasers. So, properties of lasers, have got four key ones. One is it's got a very high intensity because you'll find it's very focused over a small area there, all the energy. The second is it's highly coherent because they're going to come out in phase and also remain in phase for a long period of time, one wave behind the other. Okay, it's nearly monochromatic, so it's actually pretty much essentially one frequency, a very narrow range of frequencies, and the beams are almost unidirectional, so you're coming out together in that one direction. So that's got lots of uses. One is to read compact discs, DVDs, Blu-rays. It can weld metals because it's so intense. Use the sights on weapons, measure distances or ranges by the reflection and the time to come back. It's also used in surgery and so on, so just know a couple of those. For safety, you've got to be aware that sometimes there's a high voltage there, the gas ones, so you want to use those near water. You wouldn't show it on someone's eyes because of the intensity of the beam. The lens will focus it onto the retina and burn the retina pretty much straight away. For the same reason, you wouldn't want to reflect it off a mirrored surface because the mirror will actually reflect that pretty well into someone's eyes, so you've got to be careful to not use smooth surfaces there. You can also conduct the experiments in a well-lit room then, so your pupil stays nice and small and reduces the amount of light that would get in if it suddenly did stray to your eye. Okay? Some people wear special glasses that are just the right wavelength for that particular laser. Okay? So laser stands for light amplification by stimulated emission of radiation, LASER. So you need to look at spontaneous emission first. So instantaneous in chemistry means it happens in an instant, so an explosion all of a sudden. Spontaneous means it happens naturally without any assistance. Okay, so they're slightly different ideas. So you could have a spontaneous emission that is not instantaneous. It might take a long time for fruit to rot. It's not instantaneous, okay, but it doesn't need any help. It doesn't need to be heated up or something added to it. Stimulated emission then, now in spontaneous, by the way, we've just been talking about this idea that electrons are raised to a higher state by heating or by charging or whatever else, and they will naturally come down to a lower state and release a photon equal to the energy difference. Stimulated emission is different. You need to stimulate that to happen. So if you did have an electron that was in the raised state here, and a photon happened to come past that matched the energy difference here of 5 electron volts in this case, as that photon went past, it would stimulate the electron to go down to a lower level and release a second photon. Now what's special about this is they'll be in the same phase and in the same direction, and naturally they're the same energy and also the same frequency then, because this has to actually match that in the first place. So that's stimulated emission. Now that's very handy because that's the sort of thing we want the laser to be in. We want these to be in phase with each other, be highly coherent. So that's the sort of state we want. So to promote that, when you're building a laser, you need to find some sort of a medium which has got a metastable state, where the electrons will tend to sit in that higher state than normal for a longer period of time than normal. Okay, so metastable state is where you've got some atoms that do have those states. They sit in a particular higher state or excited state for a longer period of time than normal, and that will increase the chance of a stimulated emission rather than a spontaneous one. Because if a photon goes past one of the ground state, it'll be absorbed, go to the higher state, come back down again, you get spontaneous emission, which is no good to us. So we want to have a metastable state there. Now ideally you want to have more atoms in the metastable state than the ground state, so that you do get more stimulated emissions compared to absorptions and spontaneous ones. So we set up what's called a population inversion for that. We're going to try and set this up so that there are more atoms in the higher state than in the other one to get more stimulated ones. Okay, so how do you do that? Well, first of all, you make sure you choose a laser medium which has got a metastable state. In our case, we're going to use neon there, okay, because that does have a metastable state that's up there, and that's the role of that is to actually, or the function of that gas is to release the laser light, okay, the correct light there. It turns out that the second excited state of neon is metastable. They put helium in there to actually help that, by the way, and I'll come back to that. You need an energy pump in there, and the typical one we're using now is for a gas laser. We've got a positive electrode and a negative one, and the electrons would leave the negative one, go through the gas, strike the atoms in the gas and pump them up to that higher state, okay, on collision, all right? And if we do that correctly, we should be able to set up a population inversion where there's more elements, or sorry, more atoms in the higher state than the lower one, and give us those stimulated emissions that we want. The cavity is just got kind of like the container, and that's a sealed container. It houses the medium, and it has two mirrors on each end there, okay? One is a full mirror, one is a partial mirror, 98% reflective, 2% will come out through that end then. So what will happen here is you've got these being pumped up to a higher state, these atoms there, by the electrons. Photons that are released within here by spontaneous emission, just naturally, any that are going in this direction towards the right here, if they go past atoms in the metastable state, and they should, you'll actually get a stimulated emission occurring. You'll get a multiplication there, an amplification of the signal. Okay? If they go past more than in that direction, you get even more, and it gets amplified. It should reflect off this mirror and come back through here and do the same thing again then, and again, and again. And in that particular direction between the mirrors, on that parallel path there, you should get an amplification due to stimulated emissions. Of course, every time it encounters one on the ground state, you get an absorption, so that's no good. Okay. By the way, this is not in the course, but they do have the length here matching a multiple of half wavelengths of the light we're after, because you get a nice bit of resonance going on if it matches the right wavelength, coming backwards and forwards there. They come back in time with each other and back out in time, but that's not in the course. Okay. Also be aware that spontaneous emissions and the stimulated emissions will also come to the side here, but that's just wastage. We're focusing on the right ones that are going to come backwards and forwards through here. Okay. Anyway, that's how it works through there. Now, why is the helium in there then? So the helium is in there because if you check the two levels here, neon's metastable state is here, this second excited state here. The trouble is that when the electrons come through and bash into the neon, it tends to just knock them to this state here in many cases, and that will therefore release that energy pretty quickly by spontaneous emission, and you'll get a random photon going in one direction, any one direction or several directions, okay? And that's no good to us. So how do we ensure that we get this one raised to that state more often than the lower state? Well, it turns out that helium has its first excited state in a position that's almost exactly the same energy as that one we want for neon. So we can actually raise the helium atoms to the excited state we're after, and they happen to collide with the neons in collision there with a bit of kinetic energy. That will actually knock it straight up to the correct state, and then you can get that metastable state occurring, and you're going to get more lasing from that rather than the wastage. So it gives you more stimulated emissions rather than absorptions. Okay, thank you. Okay, so let's look at this laser then. This is a simulation from FET. Okay, so what we've got here is a couple of excited states there. We're going to use light photons here to raise these two excited states, these atoms here, and you can see it's going from ground to 1 and in some cases up to 2. And we could be using electrons instead and actually having an electrode that was positive and negative, and have the electrons come through here, strike the atoms and excite them that way. But here we're using photons, which is a bit unusual here. And if you look at that there, we've got the intensity at a certain level. So at the moment there's no mirrors there, so any stimulated emissions that are going on here, you can see coming off in pairs in some cases. There's a pair just here, okay? But we can actually sort of change this and actually improve this by putting some mirrors in. So if we enable the mirrors now, we're going to try and improve our stimulated emissions in this direction here. Now you can see then, these red ones, as they go past here, they're actually causing a stimulated emission occur, so you're getting a pair of photons now. If they go past another atom that's in the excited state, or the metastable state, you'll get another photon produced by one of those photons going past, so you get another one, and you'll see that actually amplifying as it goes backwards and forwards between the mirrors, like that now. Okay? And you can see we've got the internal power getting quite high, the output power is still pretty low. So we could actually view this as a wave view as well. And you can see here the standing wave is set up inside there because the length of the actual laser cavity here is just right to set up resonance within there. And you can see that as the wave comes out here, you're getting this nice strong wave there with good temporal coherence behind it as it goes through. Okay, and that's with the mirrors reflected at 96% on the end. So just sort of show you that one in action is working. All right. And we can go into photon view there, and you can see those pairs already increasing there. Okay, thank you.